Good evening and welcome everybody. This is Obi-Wan Paz for N-Simplex Pachinko. I can speak. We're going to be doing some more differential equations tonight. We're on night 16 and we're talking about applications of second order differential equations. So we're going to talk about, in the first instance, RLC circuit, there we go, RLC circuits. And then we're also going to have a quick chat about, parameterization, but of the polar type. So we're going to look at how, for instance, gravitation works when we've got kind of a large space available to us, and it can be in either 2 or 3 dimensions, and we don't necessarily want to have to do every single one of these calculations in 3 dimensions. It would be actually kind of easier if we could simplify it some. So that's going to be our motivation for this evening. And if our guests would like to introduce themselves, start with Zach.
Hey there, I'm Zach, Edith 2i Pi. Night 16. This has been a good ride. I'm excited to talk about this stuff tonight.
And Stucky.
All right, and I am Ian the Stucky. I'm the host of the Mathematical Creature here on Twitch, as well as the organizer for No Royal Road, a geometry study blog.
Alrighty. I know I signed up for the subscription or whatever it is,
saw that.
to make sure that I would get updates on that. So I'm looking forward to it.
I was gonna say I forgot you could do that. That's right. So it's a newsletter, right? Actually, I'm gonna go do that right now. Actually, because that's a great idea. I hadn't even thought to do it. Right? I just was like, oh, I'm gonna go check this every so often. But guess what? We can subscribe.
Yeah.
So if anybody is interested, head on over there. And if you're on Stucky's Discord or oops.
On Zach's Discord.
Yep, so if you have either of those, we're also using Penn Center's Discord as our medium over which we speak. So if anyone is interested in going to any of those 3 places and hooking yourself up with access to all of our Twitch math people, those are the kind of main 3 for everybody who's here tonight. And here's our giant list of everybody. I shouldn't say everybody. It's not everybody, but this is mostly our kind of core group of people who do math on their individual channels on usually some night of the week. So,
And I would say this list is growing.
Yes,
I know that
that
there
is
have
true.
been some who have come and added to our group. So, and we invite more to join us.
Yep. So if you are a Twitch math streamer, please contact any of us. Get in contact on our Discords, and we'll be happy to have a chat with you and hopefully get you entered into the community as well. And good evening to Holonomi.
Hello, Olonomi.
And everybody else who's out there.
I recognize geometry here. Holonomy? Is that right? Is that how it's said? I don't know if it's. I think that's right. I remember parallel transport and stuff. There's a whole bunch of there's some geometry stuff I've seen before with that.
I don't think I got to that particular section. So.
Yeah, good times.
And yet again, make sure you actually hook stuff up before you start. Oh, man.
Classic.
Alrighty, so we have... For tonight, we have the applications we're going to look at. Come on now. Man, that's awesome. For some reason, I cannot find the exact section in my notes. I had it up just the other day. Alright, apologies everybody. Let's see. So last class, what was it we were talking about?
Let me see here. I left a little early. So I remember we did some stuff with second order differential equations. And I believe we were trying to... It was with physics. That's right. We were trying to build the mass spring model and solve the mass spring model and talk about damping, right? Not like the... if I saw the end of the VOD correctly, that's... I cut off right before you started talking about damping and such, but I remember something about that.
Yep, and we were mostly talking about springs attached to spring mass systems to make sure that we connected the idea with second order differential equations with F equals ma, right? We had talked about then how the acceleration is in fact the second derivative of our initial x function that we're trying to look for in the first place. And then we talked about damped and undamped systems to add in our middle term, so our x prime. I also did an example offline that worked with the damped system to try and work out, or to show the two separate types of solutions we get. That is also some interesting vocabulary, which I don't know if anybody else learned it differently. Because when I was in school myself, it was not called these two things, but... Well, sorry about that. We're not going to get it, so that's fine. With the various motions we had, hey lads, with the various motions we had, we said that we could have pretty much either. We're going to go with a positive initial value here. So we could have an overdamped system, which even given a massive initial value would sink very quickly towards 0. This would be a rather jarring experience if you were involved in some sort of overdamped system. This is, for instance, like a car's shocks. If they're set too high, basically when you hit a bump, they just kind of like will allow you to hit that bump and then sink almost directly into the rest state of the car. It would, like I said, it'd be rather jarring. There is also the underdamped system, which would basically allow... That's not to scale. Ooh. The underdamped system would potentially allow this to spread out a lot over time. We don't have to have such a crunched in version like I have here, but this would essentially have us going up and down past equilibrium multiple times. It doesn't have to be a simple oscillator like this one. It could also be one that goes and changes its amplitude over time. So something like this, which sinks down to 0 back to the equilibrium, is also underdamped as well. Alright, and then we have the awesome one, which is our critically damped system. I'm going to have to rewrite this somewhere else. It's just getting too busy. So our critically damped system will look sort of like the overdamped, but at the same time, as it starts sinking down, it's almost linear in the way that it sinks toward its equilibrium, rather than the very clearly exponential version that we have for the overdamped. And in a lot of systems, this is the way that you minimize any sort of damage to either the door or the door jamb or the dashpot that we were talking about last time. And yeah, as soon as you left, Zach, I was like, that thing, couldn't remember the word for it again.
The dashpot, yeah.
Yeah.
That's been my new favorite. That's been like one of my favorite words with regards to differential equations and engineering and such. Is dashpot. When I discovered it, I thought this puts everything together for me. Mm-hmm. So I had to share.
And it's such a perfect example of critically damped, or you could do anything with it, but trying to like fine tune a particular system to make a critically damped. I mean, it's not an oscillator, but like the class of things is called an oscillator. And I also said, like, you could have a severely underdamped system, which would be more like your saloon doors. So something that flops back and forth quite a ways for some time before settling back into equilibrium.
That's really interesting. I hadn't thought about that one. But that's a good example. I like that.
Yeah.
And I really like the mechanism for that one because it's like a regular hinge, but it's allowed to grind against the side of the holder part of it, and when it's swinging, it's like actually moving upward, grinding along the side of it, so that when it swings this way, it can't swing like all the way out unless you really give it a shove. But and then as it grinds against it coming the other way, it's going to naturally start losing its momentum, and it's going to start like having this, like the green underdamped system here, the amplitude will keep shrinking until it reaches 0 or reaches equilibrium.
That's really neat.
Yeah.
I've spent a lot of time watching those doors. As a kid,
Well,
like our favorite restaurant had one of them, and I was just like hypnotized by it. It was great.
yeah. Well, and it reminds me of like every time I see one of those accessibility doors that like you press the button and it'll open
Mm-hmm.
for people gradually for like wheelchairs and others. Those are like those critically damped, right? You're trying to keep things safe, and that's actually I was actually reading into specifications for
Mm-hmm.
that because I'm curious like how they determine stuff like that in practice.
Yeah.
Which is I was actually when I got to teach differential equations once at my current university, and I was going to do a project about that because I was trying to find a practical reason why we care about this stuff.
Mm-hmm.
I just couldn't get the project to work. I couldn't get the technical details right. But in principle, I wanted to do something with this. And now that you mentioned like saloon doors, we could have had fun with lots of door styles. I think that this could have been a fun project. So anyway,
Saloon doors, very much not accessible.
no, I know, but I'm saying that this is like the math in the real world that people want,
Yeah.
right? Anyway. Maybe for another day, if I do a different class on Twitch, maybe we'll do like I don't know. That could be fun.
All right, so typically when we have now any electrical engineers out there are probably going to yell at me at some point. So get your fingers ready on your keyboard because I'm sure it's going to be pretty awful at some point. I'm going to say something that's going to upset somebody. Okay. Your math is called abstract nonsense. Yep, okay. R is for resistor. So here we have a resistor, which in the context of a circuit is going to sort of hold back a certain amount of electrical potential, I think it is. It's going to, if the electrical potential is low enough, the resistor will prevent electrical potential from moving from one side to the other. I think that is correct. If anybody knows better, please correct me.
You say what you said one more time, just to make sure I followed. No,
Just to make sure that I'm
I
wrong.
didn't follow it. I didn't. I like somehow missed the end of the sentence. So.
Yeah. So you've got a resistor which is going to resist electrical potential. So if there is a small enough electrical potential on the one side of it, and in theory, it could be either on the positive or the negatively charged side.
So far, I'm with you. That's my understanding.
Oop, wait a minute. Oh boy. Hang on. Nope, that was the other way. There you go. Alright. Oop. Yeah, okay. They're all the same except the switch, oddly enough, is the other way. Okay. So if the electrical potential is low enough on the positive side of the resistor, in theory it could be either side, but whatever, it's going to resist that electrical potential's motion to try to get to the other side, and it will have a net zero potential on the opposite side. So it's not going to allow this, what we consider electrical flow, but realistically we're just looking at the potential. So it's sort of like a charge density, I want to say. Again, if I'm wrong, please correct me, anybody. Of all the times not to have an electrical engineer as a friend around, right?
I was gonna say, where's Mary in all this? We need Mary here.
He would gladly yell at me. Okay, so we have here an inductor, which is going to be short, or listed as L, is the inductance. Now, I don't understand inductance just from like a word point of view. Right, tendency of an electrical conductor to oppose change in electrical current flowing through it. Alright, so if the current increases, then a voltage opposing that change is created by the coil. Okay. Whereas resistance is a constant put. Okay, there we go. This is also what's going to help is like how do these things interact with each other. So resistance is a constant pushback, sort of like friction. Inductance, on the other hand, is resistance to a change in the electrical force, more akin to inertia. So high inductance is like high inertia, high resistance is like high friction. I think this is going to work the best in terms of trying to find a analog for how these connect to, RLC circuits connect to our spring mass system model.
And yeah, you're talking about the resistance that instantly makes me think of that linear or the first order derivative.
Yep.
Right. Just sort of in the same spirit how we had mdv dt,
Mm-hmm.
or what is it? It wasn't m. It was a gamma. That's right, gamma dv dt. At least that's the tradition.
And then we have our capacitors with capacitance C. That's how much charge this particular item can hold before it's either going to max out a charge and then it is going to... I think it's going to start resisting based on how much charge is inside of it, unless it gets discharged. And let's just also get that in here. Yeah, capacitance is the amount of charge that can be stored at a given voltage by an electrical component capacitor in farads. Capacitance is in farads. And capacitors can hold certain amounts of voltage, can be charged to a certain voltage, holding certain number of coulombs of charge. So there's going to be a lot of unit analysis going on, but overall we don't necessarily have to know every little bit about it. As mathematicians, no.
But the physics here, I think, is sort of like you're making me think about how we could build a differential equation, right? That that you have charge, which is sort of your function q, right? And then you're going to have some dq dt, which is your rate of change, and that's like the gamma term with paralleling here with the resistance. And then you're going to have your acceleration term, which sort of mirrors this inductance, right?
Mm-hmm.
And the way you're describing it makes me think about all three of those things in relation to the mass spring model.
And it's also really fun to switch on a battery or generator and then look at what happens to the voltmeter. I don't know if you've ever noticed, but if you hook up a voltmeter onto a like a analog voltmeter, so one that has the little needles that fling back and forth, you can actually flip on the generator and then watch as it like zooms up to a particular voltage and then just kind of like oscillates back and forth until it hits the mark. So it is very much like a typically damped oscillator. Like the voltage in the system will overshoot, then undershoot, and then get pretty close to the correct value. Most of the time I think it's underdamped, but sinking toward equilibrium pretty quickly. Sometimes you'll get a critically damped one, which will just move toward equilibrium, again, almost at a linear rate. And again, I think that in order to not shock the system, the...
Well played. Well played.
I totally didn't even mean that. So I think in order to not, like, damage electronics, you try to get a critically damped system so that the charge will build at a more steady rate, rather than overcharging and then undercharging in the same short time. So our generator is going to have an impressed voltage, which is termed usually E of T. In addition to the voltage, we also have the current. I of T, that's running through the electronics. So I've had this sort of termed like the voltage is sort of like the amount of water within a particular, pipe, and the current is the size of the pipe. So based on, and again, this is a terrible analog, but it can work for like somebody who doesn't know how electricity works more fully. That would be me. So you have a certain amount of water that's trying to get through the pipe, and our voltage can then create an analog to that. A certain amount of charge is trying to get through the pipe, and our current is going to be the size of the pipe. So the larger the current, the more charge can get through. But then also, like, all of this stuff can be kind of fine-tuned to be exactly what you want for your particular application. If anybody wants to pick up on this, feel free.
It's interesting because Holonomy made this exact same observation in some ways in chat.
So that's kind of almost like increasing your resistance is going to make the water pipe smaller. So that's also going to increase the pressure in a water system. I'm not sure if that has an analog in the electrical system. And if there is, definitely share that, because I feel like it does, and I can't remember. Alright, I is going to be greater than 0 if the direction of flow is around the circuit from positive terminal of the battery around this way to the negative terminal of the battery. So we're looking at the switch. While the switch is open, nothing's happening because it's an open circuit. Once you close the switch, it becomes a closed circuit, and then we can start having the electrical potential or voltage actually count for something. I is going to be 0 if no current is flowing, and I is going to be negative if the flow is going from negative to positive. Okay. Now, with all of these being labeled as positive and negative, it isn't strictly going to be like, oh, the protons are more on this side and the electrons are more on this side. Really what's happening is that through the medium that you have, whether it be a resistor, inductor, capacitor, or a battery, we're going to have a higher electrical voltage, a larger E of T value on each of these places, which has a plus. And then we're looking at the voltage drop across each of these components. So this is where the differential equation starts coming in. Alright, so this voltage drop across the components is going to impart this electrical potential and be like, oh, look, now we've got higher amounts of electricity in each of these places, and the voltage drop across a resistor is going to be equal to the current times the resistance. The voltage drop across an inductor, that should not be an I. Let's make it an L. Anybody know where L comes from? I mean, it's inductance, but like...
Yeah.
Is it a different language?
Apparently, it is in honor of the physicist Heinrich Lenz.
Ah, that would do
It was
it.
named after somebody.
L-E-N-Z?
Lenz, yeah. So says the source of all knowledge, Wikipedia.
So the voltage drop across an inductor is going to be our inductance times the change in the current. See, this is why I didn't want to use a capital I. Is going to be our inductance times di dt, the change in the current, which is just going to be L times I prime if we want to use that. It kind of depends on what variables we're going to be using as we go through this whole thing. And the voltage drop across a capacitor is going to be given by Q over C, where C is our capacitance and Q is going to be the voltage at any particular location. Just check that. Capacitor stores electrical charge Q of T. Okay. So, with this, we've got quite a few different units that we're using. We've got E, which is the impressed voltage. Which uses volts. We've got I, which is the current, which uses amperes. Q is the charge, and that one's going to use coulombs. R is resistance, which uses ohms. L is our inductance, which uses henries.
This for me was always the hardest part, was keeping track of all the units.
Yup. Especially since they're not like, you know, newtons are kilogram meters per second squared, so like you can break this down super easy. Here it's like, great, they're all named after people. It's, you know, not something you're going to be using no matter what science you're using. It's like these are very specific to electrical systems. All right, capacitance, which is in farads. Now the good news is that we do have a conversion. So volts is going to be ampere ohms, or Henry ampere per second, or coulombs per farad, and ampere is going to be coulombs per second. So in theory, if you're good with your unit analysis and you've got like all of this stuff here, you could be able to figure out how this whole system is going to potentially work. Just by on the basis of unit analysis alone. I'm not that guy, but so what we have is that there is a statement called Kirchhoff's law, which says that the sum of the voltage drops around a closed circuit and this does have to be just a simple RLC circuit, only using some or all of these particular components. If it has other stuff like an oscillator, we're not going to be able to use Kirchhoff's law directly. There has to be some sort of modification to it. Is going to be equal to the impressed charge. Sorry, impressed voltage. Wrong word. E of t. So we're going to look at all the little bits that we left up there. So our voltage drop across resistors, plus the voltage drop across our inductors, plus the voltage drop across the capacitors, has to be equal to E of t. If we go with what we had up above, we got IR plus arg. That one. L times I prime plus V sub C was Q over C is equal to E of T. So this gets us our Kirchhoff's law. We can also then state, well, our variable that we have here in terms of a differential is going to be I, and we have I prime. So we can kind of rearrange stuff to make it L times I prime plus R times I. And at the moment we could move stuff around a little bit. I'm going to keep Q because Q is its own function. It is not going to be a function only of the independent variable. See why in just a second. Alright, so from what we have here, we know that I is going to be the current in the circuit. And we know that Q is going to be the charge in the capacitor. And anybody know the relationship between these two things?
The current is the change in charge over time.
Yeah, so I is going to be Q prime. So in this case, we could say, right, the change in the charge is going to be the current that's running through the circuit. So we can actually change out I for each of here Q prime and here Q double prime. And lo and behold, we have it. Okay, so the sum of the voltage drops across each of the components is going to be equal to our impressed voltage, E of t. We found what each of those voltage drops is going to be in terms of either I prime, or Q. And then as it turned out, I is just the same as Q prime, therefore I prime is going to be Q double prime. And then we can substitute in. We end up now with a second order differential equation. And do you want to classify any of the rest of it?
So it's second order. Ordinary. It's non-homogeneous because as long as E of t has a forcing like sinusoid. If E of t is 0, then it's homogeneous.
And it's linear.
Yep, because our inductance L, our resistance R, and our capacitance C are all going to be constants for this particular setup. None of those things are going to be variable by the nature of inductors, resistors, and capacitors. As I said, if you have an oscillator or some other type of component that is not listed here, then you could have all sorts of other stuff, and this differential equation does not apply. So we could end up with a variable resistor, for example. But like I said, it's not going to work for us. We're not going to be able to come up with the same stuff, and then we're not going to be able to solve it in the same way. Alright, so let's go with a particular kind of problem. Alright, so at t equals 0, a current of 2 amperes is applied through an RLC circuit with resistance 40 ohms, inductance is 0.2 henries, and yes, it is YS rather than IES. Because it is somebody's name, they don't change it to IE at the end instead of Y. And capacitance, 10 to the negative 5th farads. Find the current flowing in the circuit at t is greater than 0 if the initial charge on the capacitor is 1 coulomb. Assume that E of t is going to be equal to 0 for all t greater than 0. Alrighty. Discuss.
Well, it looks like we've got some constants that are gonna fit with the equation we just wrote down.
Oh, I'm sorry. Could also like start the session and copy the link and stuff. Sorry about that. A.
See. So, before R1 over C. So the from the assumption our right hand side is 0. Q is not exactly what we want. We want current. But that's Q prime. So we'll treat Q as the variable. And then for the rest, we've got two of those. The resistance is big. And the capacitance is small, but it's 1 over the capacitance, so that's big. Okay. And the 5th. How many zeros is that? 5 zeros, 4 zeros. Let's get this one wrong. Yeah. Okay, well. This hoping maybe I could factor that, but it's not so clear.
Yeah, 500,000 having this would have to have the same signs, given that the 500,000 is positive, and then to have a number as small as 200 as the sum of those two numbers.
Right. So that gives us
let's see here, negative 200, and then gosh, 200 squared is 40,000.
I'll take it.
And then it'd be 2 times 10 to the 6th is 4 times 5 times 10 to the 10 to the 5th. And then over 2, right?
Yeah. Which is massively negative.
But hey, I mean, it's a thing. It's a number.
Sure is.
10 to the 4th and 2 are factors. So,
yeah.
and then 100 comes out, yep. So, that seems like I agree. Let me think about that for a second, because you factored out a 4, so is that right? Like we're factoring out a 4?
Yeah.
Okay. So you factor out 4, then the 2 wouldn't be there. That would be a 1, yes?
That's a 1. Yeah.
It's a 1. 200 factor off 4 is 50. Okay, I was trying to get the 50. That took a few more steps in my head, but I'm okay with it.
Yeah, safe.
That will be 7i. Yes, so 100, negative 100 plus, I guess, minus 1 plus minus 7i. Yeah, I agree. Which means that we have complex solutions. So you have an e and a cosine. E to the minus 100t, I think.
So in my notes, my ratio between first and the real and imaginary terms is 1 to 2.
Woof.
Woof. Yeah, I was gonna say.
So I think when you took out 10 to the 4th, you dropped off an extra 0 somewhere. No, maybe not.
I don't think so.
By the way, Obi, it's about time I have to duck out.
Yep.
Because we're at the halfway point. But thank you for hosting this.
Yeah. Thanks for coming.
I appreciate it, and we'll see you Monday. Right? That's the next time you're.
Yep. That's the next time we're definitely doing math. And I'll be on one of your channels between now and then, I'm sure.
Okay. Yeah. Fair enough. All right.
All right. See you later.
See you, Zach.
Yeah. No problem. And there is a question in chat if you want to take a look at it.
I'm looking
it's actually relevant to differential equations. It's like.
It's true.
So, unlegit Apple. Let's see. So if we have this particular 4th degree polynomial, yep, diagonalization of a matrix could be an option. I'd say for this one, you might actually even just fall back on some pre-calc stuff. So if you were to plug that into just even a graph and then do synthetic division and knock out any of the obvious ones that you can find. If there aren't any, that's fair. Hey, Megalomorph. Yep, that's the way that I would do it. Now, I grant you, I've been teaching pre-calc for 15 years, so hey, thank you so much for the Prime subscription. And anybody else out there who does have Prime, you can drop that on any one of your favorite streamers out there in the world. They would be very happy to accept Jeff Bezos' money. Yeah, so it's the old adage of when you're a hammer, everything looks like a nail. I've taught pre-calc for a long time, so I try to pretty much bring everything back to function analysis and pre-calculus. If it doesn't happen, right, there are other methods, but for the most part, even with my differential equation students, I would usually be like, all right, well, let's just double check this real quick to see if it works as a rational roots, and then if we can knock out 2 of them, then we've got a quadratic. We could just solve it very nicely. If it doesn't have rational roots and everything is either irrational or some weird complex that you're not just going to be able to guess, then yeah, you might be a little bit more challenged. You could also try looking at the phase plane of higher degree. That's a silly thing to say because that would have to be 4-dimensional. A. Yeah, if it were 2 or 3-dimensional, maybe take a look at the phase plane and see if there was anything that popped out in terms of like steady state vectors, because that would be your eigenvectors. You might be able to figure out something about the eigenvalues from that. But yeah, like I said, I would probably go with pre-calc methods. Look for rational roots and see if you got anything there. All right, Stooky, what do we have?
Just continuing to roll, but I do like this 7 number, so.
Oh, interesting. Oh. Is that what happened? Just double check this real fast. I think there might be a printing error in the book. So this is 10 to the negative 5th, which is going to be 1 over, no, 0 0.1, 2, 3, 4. Right? 1, 2, 3, 4, 5. So this is 1 over 10, 100,000, 10,000, 100,000. Yeah. 1 over 10 to the 5th. Yeah. Yeah, I think there's a printing error in the book. So my notes are wrong.
Hey,
Yay!
it might be the first time, actually. The notes have been pretty high quality, despite my best efforts.
All right, just to let everybody know, we got an ad break coming up. We'll finish this one up and then do some discussion, maybe while we're offline here, and then not offline, but while we're on break, and then we'll be back in just 3 minutes. So hang on. Thank you very much. See you in a bit. Alrighty. Right, because that was... one other small thing.
Okay.
You factored out a negative 100 from everything?
Yeah, I see.
Unlegit, you're still here, I assume. What's your background? And we're back. Thanks everybody for sticking around, and Stuki's been finishing this last bit up here.
Yeah, so we plugged in initial conditions, which were the 1 coulomb on the capacitor at the beginning, and then, so that's the charge, and then the current of 2 amps at the beginning, which is Q prime, and so we just solve for constants, and we're about to write down the thing.
Yeah, so this is one of the convenient things about initial value problems, especially with sines and cosines, is that at Q at 0, one of them is going to drop away and you just get what the A value is, what one of your constants is. And then in the next case, you've got Q prime, so you take the derivative and the other one is sine versus cosine, and the other one drops out, so you get B. So we do get our 2 equations here. Right, so the current I of t is going to be equal to 700 e to the negative 100t sine of 700t plus 2 e to the negative 100t sine of 700 cosine of 700t.
Oh yeah.
Push that over a little bit. All right, and in doing so, now we show that, again, this is the current that is within this particular RLC circuit, and a lot of times they will ask for the charge. So you're looking for what's the charge on the capacitor over time. That's Q of t. So in this case, being, what is Q prime of t? What's the current in the entire system? It's pretty much the same amount of work regardless of which one you're doing. You still need to find all of your constants, and then you still needed to have Q and Q prime in order to figure out what those things were, what those constants out front were. So whether they're asking for what's the charge on the capacitor at any given moment, or what is the current in the whole system over time, again, same amount of work, same basic process. It's just which one you're ending with. All right. Did you have any questions, comments?
You have any idea if these numbers are reasonable? Like, I vaguely remember that farads are like super big units. So it's not super surprising to me that it's that small, but that might even be big.
I want to say yes, but so if we do, like, let's go over to Desmos here. I of t is equal to, can you read that off for me? It was 700.
Yeah, 700 e to the negative 100. Fine.
Sine of 700t plus 2 e to the same cosine of the same. Right. So
well, yeah.
if we go with from negative 700 to 700, okay, let's do 1700, okay? Cool.
Oh, the cosine needs a negative on the exponential. That's why that's happening.
Ah. There we go. Much better. Thank you. X goes from 0 to, yeah, I mean, even like 0.1. And this is not even 600, so that's good. So we have here 1/10 of 1 second, and once the switch is thrown on this particular electrical device, we have that the voltage will reach within, here we had 6.3. So this is approximately 1% of the initial, this is current, of the initial current flow. The high point at the beginning is 565 amps. Now it only does that for a very, very short time. And then by 0.05 seconds, or just after it, it reaches a maximum of negative 4 amps, right? Or a maximum distance of 4 amps. So I'm not like 100% sure, like, of the reasonableness, I guess, of that particular thing happening. To me, this does seem like a little bit of a, punch to the system here. Because most of our circuit breakers, for example, are something between 10 and 40 amps. So if we have a 2 amp current that's been pushed into the system, having it jump to almost 600 even for a really, really short amount of time seems really harsh, but I can't speak to that necessarily just because I don't think I have enough experience.
Yeah, fair enough.
But also, if we go with the incorrect thing that the guy put in the book, right, the solution ended up being 2 cosine and negative 251 sine. And positive 2, yeah, positive 2 cosine. So here, the instantaneous current is only 200 amps. It's a third, basically, of what we had before. Still kind of a lot when you think about, again, in terms of... well, hang on. This is also supposed to only be, according to, again, the incorrect stuff that he had, only 200 T. Oops. No, that's right. Okay, so again, it sinks it even further. So 128 amps. Again, still seems like a lot, but this is, again, an instantaneous current rather than like one that's going to be rather than our equilibrium. No, I mean the equilibrium is essentially 0. I think I have intuitive problems with this. Like my intuition is not here for this particular kind of problem. I will freely admit that I generally stay away from electricity because I'm not typically very good with it, but had some bad experiences in the past. Yay! Yeah, I was 3 when I decided to try and reach behind a plugged-in nightlight. That was not fun. All right. Anybody out there have any other questions? Your family was shocked to discover you were bad with electricity. Yeah. Thank you, Megalomorph. I can always count on you.
It's true.
I also have one here. No, you know what? That doesn't work. Cool. All right. So if we were to look at if we end up having a differential equation that has an E of t function that is not 0. So if we had said here that our impressed voltage was, again, anything but 0, Zach was correct most of the time. You're going to see some other sine cosine function over there, just because electrical current works off of oscillation. So our alternating current system has, again, a current that alternates, where it both sort of, again, this is an analogy and probably a bad one at that, but sort of pulls and pushes the electrical potential back and forth. I know Veritasium, Derek on YouTube, did a demonstration of it where it was like a chain being pulled through a tube to represent a alternating current system, and several electrical engineering professors came on and were like, yeah, it's not really how that works, but I was like, okay. Oh well. But the electrical potential essentially works from both sides of the circuit, but then alternating. So it goes on one side, then it goes on the other, then it goes on one side, then it goes on the other. So we get, as we saw with the Desmos picture here, a current which is both positive and negative over different time intervals. All right, the next thing. Nope. All right, there we go. So the next thing we wanted to look at were what are the possibilities if we have something called a central force. So in this case, we're going to be looking at an object which we will consider at the origin, just because we always do that. And in this case, this is going to be a astronomical body. It has some actual size to it, but over a large enough area, we can look at this and say, you know what, it's close enough to a point mass, as long as the x and y units are big enough that it's not going to make a difference. The point here is that this central force, in this case we're talking gravity. We could also have magnetism, electrical charge, and the list will go on. I definitely don't have an exhaustive list anywhere, but the size or magnitude. That's an I, isn't it? Is based only on the distance to the origin point in this particular case. We're just going to call it the origin point and assume that the any other points that are out in space are not going to exert a significant force back on the object at the origin. So it is not effectively going to move anywhere. So at this point, we could have a force that more or less looks like this. Uh-oh. Hello?
Hello.
That is not me. Could have a force that looks like this, and then as we move away, this will end up being this will end up decreasing as the square of the distance. So we end up with a much smaller force as we end up going away from the central points. Obviously, I do not do a good job with making them smaller. But again, this is our idea. As we move away, the only thing that matters is going to be the direct linear distance between the origin point and our current point, wherever we are. So if we have a point xy in space, then the force, the gravitational force, the magnetic force, whatever we've got, is going to then be proportional to again, this one was going to be 1 over d squared. So can you think of any particular good way to do this?
Well, with we're just dropping that and seeing where it goes.
How do you mean?
Like this test mass or test charge, and we want to see how it flows along this.
It'll always move in a direct line distance, provided that its motion in any other direction is 0.
Sure. Then I must have misunderstood the question.
So is there going to be a good way to devise, for instance, if either we pick any random point in space and then drop it and watch it move directly toward the origin, or if we choose an initial value for the velocity of this object, which is not 0, is there going to be a good way to model its motion either toward or around the origin point?
I see.
It's like, would that be convenient to do with our current coordinate system?
No.
Why not?
Well, I don't know how to explain that. It's just, I guess the best case where it's not purely in the radial direction is when it's when it ends up traveling in a circle. But I mean, even this is not so pleasant, right?
Mm-hmm.
X and Y coordinates.
Right, so if you do have a potentially circular path, so we already know that there is the possibility to throw this object xy at a particular location in space with a particular velocity from wherever it is at its initial point, such that the forces will directly equal each other, and we end up in a perfectly circular orbit. And at that point, you'd want to say, okay, look, if we're gonna do this and have like this perfectly circular orbit, I don't know about you, but I don't really want to work with x and y, because that ends up being a complicated non-function, at least non-function y in terms of x. And we could probably come up with a better method of doing this, or a better coordinate system in which this all simplifies. Got any preferences?
I like polar as an option.
Yeah, and especially if we're doing something with, again, potential circles, or due to the fact that we have here, this is due, our size or magnitude of these particular forces are only going to be based on the distance away from the origin that they exist. So the distance from the origin, again, are inversely proportional to the distance squared. We could also call that the radius. And then that could give us our polar coordinates. Okay, so typically our cosine of theta is going to be equal to
X. Or X over R.
right, x over r, because we're looking at this in terms of creating our oh, you know what, I've already got a point out there. Let's use the point. Right, we've got a point. If you draw a vector that goes from the origin out to our point, then it has components, right, x and y, and r the radius. And we'd also have then some theta, which is going to be our angle here. And lo and behold, we're back to trig. So we have our x and y components there. They're at right angles to each other, orthogonal naturally. And then we have our directions, I hat and j hat. Okay, so the cosine of theta was going to be x over r from here and here, and our sine of theta is going to be y over r from those. Naturally, if we're starting from rectangular coordinates, then we're going to have stuff only in terms of x's, and so this can be r times the cosine of theta, and similarly for y being r times sine of theta. Sorry, I'm trying to reverse engineer something.
Okay.
Alright, so then we want to come up with what our force is as a vector at any given moment in time. If we do it in terms of r and theta, then there is going to be a there's going to be a function f of r, which is going to describe the magnitude of the force at any particular location, often space. Again, only dependent upon the r value, so our distance away from the origin, r. Right, and then we have two terms which are going to be cosine of theta times I hat. So this is telling us that we're going to take our I would probably say normalized x over r distance, which is cosine of theta, times I. It's also our component of the normalized vector, and the sine of theta j hat. It's not really times, but it's in those directions. Alright, Stuki, you got any comments?
Don't think so. Yeah, I don't think so.
Okay. So we're going to go back to a lot of similar stuff, what we were saying last class with Zach, in terms of let's back all of this up to Newton's second law of motion, which is that the sum of the forces needs to be equal to our I. Needs to be equal to our mass of the system times the overall acceleration of that system. So what we were able to pick up from last time was that we had, for this system here, our mass is going to be multiplied by our acceleration, which is also mass times position's second derivative. So the position of any particular mass in this system is going to be xi hat plus y j hat, which then can be double prime, which can be rewritten in polar form. X is instead r cosine theta I hat plus y is instead r sine theta j hat. And then we double prime that because, again, we want the second derivative of the position, which gets us our acceleration. That is then going to be equal to our force that we had from above. Which is F at R times just cosine theta I hat plus sine theta j hat. Okay. What we're going to do is, in order to derive this, we're going to introduce unit vectors E1, which is going to represent cosine theta I hat plus sine theta j hat. Wow. And E2, which is the derivative of this. So negative sine theta I hat plus cosine theta j hat. It should also be noted that if we end up with E1 dotted with E2, or just multiplied together through our vector multiplication, so dotted, but this is going to end up being
Zero.
Cosine theta I hat, yep. No more I. Cosine theta times negative sine theta plus sine theta cosine theta, which is 0. Okay. So if we rewrite the above relationship, this is going to end up being m times RE1 and RE1 is going to be double prime equal to f of r times E1 Our E1 double prime, we should also mention, right? Or I did sort of mention. E1 prime was going to be equal to E2. And E2 prime ends up being what?
Negative E1.
Yeah. Right, so with that in mind, we've now got M times, we could do a product rule on this. So R prime E1 plus R E1 prime is just going to be E2 . And then that's also going to be prime from there. M times. If we take the derivative again, these are product rules again. So this is going to be R double prime E1 plus, and then we end up with another R prime, and then we take the derivative of E1 and we get E2 again. Then our second one, we end up taking the derivative of R prime. Ooh. And then we end up taking the derivative of E2, and we get negative E1. So that's now negative there. Is equal to f of r times E1. All right. Do you have any arguments?
Don't think so.
I may. Ah. Yes. I forgot something. So these are also functions themselves of theta. So while we're taking the derivatives of these things, that's also going to cause us to need to use the chain rule. So every time we take the derivative of one of our e's, we also need to incorporate theta prime as part of the chain rule.
Okay.
My fault. Okay, so this one we did not do any. This one we just did one. This one we also just did one. And this one we did two. Alright, so now if we try to get our e's back to some semblance of sanity, we're going to get m times the quantity. E1s are going to be r double prime minus r times theta prime squared. And that's all E1. And then also, this is still M. We have a plus. That should just be two of those things, right?
Looks like it.
Oh no. Yep, I think I messed up again. Sorry, Stooky. Okay.
Oh, I see.
Yeah, in our second term there, that's a three-way chain rule. So we need to do all three of these. So R prime, then E2, then theta prime, then E2 becomes negative E1 theta prime times theta prime becomes theta prime squared. Then plus R E2 theta double prime. Okay. My bad. So good news. Those now belong together. So we've got R prime, theta prime,
Yeah.
Plus R theta double prime. That's all E2.
So two of that first term.
Yes, right. I even saw that. Told myself I wouldn't forget it. Okay, and that is f of r times E1 still. Alright, so now it's down to equaling coefficients again, so just like we did all the way back for decomposition, partial fraction decomposition, and all these other things that we absolutely love to do. Right, we end up with m times r double prime minus r times theta prime squared is multiplied by E1, which on the right is going to be f of r. So our two coefficients need to be the same. And a coupled system of equations, the second term has to have the same coefficient on E2, which on the right is 0. So an E1 equation and an E2 equation, just in case you need to clarify that sometimes that's a nice little thing to do. Alright, this also has an m. And then we're multiplying by 2 r prime theta prime plus r theta double prime. In this case, we don't need the m, just because it's going to divide off and get us a 0 anyway. On the right. Alright, and Since r, I believe, is a function of theta. Did I say that? No. We did not do that. That's fine. We'll leave it there. Our second equation here can be multiplied by r.
There it is. Okay.
To get r squared theta double prime plus 2r r prime theta prime still equal to 0, which is the same as I don't want to use that notation is nice, but we're not going to do that just yet. This is going to be the same as r squared theta prime all primed equal to 0. So from here we can solve the differential equation that's been created by our second equation based on E2. So r squared theta prime is equal to some sort of constant. And then we can do separation of variables. So theta prime is equal to c over r squared.
Yeah, and I'd like to leave it there.
Yeah. Okay. So this is going to create a interestingly, yes, it will actually create a better system. Nah, that's all right. I will attempt to explain this better. Well,
I mean, I think we're just there, right? You can shove that into the first equation. Life is good.
oh, yeah, because we have theta prime. Yep, and everything is
Yeah.
in terms of everything's in terms of r. Yes. Okay. Right. Thank you.
Sure.
Right. You don't have to solve this. We're all good. Alrighty. Stuki, thank you so much.
Yeah,
And
thank you.
thank you, Zach, for coming in as well. We will be back for more differential equations on Monday, and then again on Wednesday next week. We're going to start getting into our numerical methods and saying, hey, what's going to happen when you can't solve differential equations terribly nicely? So we're going to see a lot of whether linear or nonlinear differential equations, but just ones that are not going to be convenient by any method that we've seen thus far.
All right.
So we'll start with series solutions. And then we'll be back on Tuesday for more mathy type stuff, and Friday for more gamey type stuff. Stuki, if you want to plug your channel, go for it.
Sure. Yeah, so we should be live this weekend, probably Friday, and a few hours ago. And also tomorrow will be the next update from the Substack, so if you want to go subscribe over there, that's enstucky, same as the Twitch name, .substack.com.
Right. I'll pop that in the chat as well since we're here. There we go. All right. And so I will see you at some point, and probably before Monday. We'll see.
Sounds good.
Alrighty.
Take care, Obi.
Yep. Thanks, Dookie. Have a good one.
You too.
All right. If there are any last-minute questions, we can work on that. Otherwise, I think we're probably gonna. We got 5 minutes left before another ad break. I probably want to get you out of here before that. But if anybody has any quick questions, I can answer something. Let's see, is anyone else on for math? Does not look like it at the moment, so I think probably we will go over and see Astro Canuck again. He is currently waiting for astrophotography to be or waiting for the light outside to play a little bit nicer so that he can do some astrophotography tonight. Currently, he's putting together some giant Legos. He like 3D printed some giant Lego people, and that is it's it just went offline. Just okay. Go check out Astro Canuck. Tom's a very wonderful guy and does some cool stuff. Astrophotography, woo! I think tonight we'll... Alright, well, we'll head over to Peace, Love, and Jody, who's doing some Elite Dangerous. And, yeah, I know, darn. And if you want to stick around, great. If you don't, that's fine. Hope to see you all on Friday for gamey type stuff, or next Monday for our next differential equations class. Again, series solutions. So we're going to start out mostly with, solving differential equations by using series. Somewhat similar to your Calculus 2 type stuff where we were using Taylor's series. Just saying. So I hope you all have a good week. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you over there.